We are continuing with Charles' law. In this video, we are going to be talking about the graphical representation of Charles' law. So we know the equation is Vt, okay, let's just write that. Vt equals to V0 of 1 minus, oh, sorry. Okay, 273.15 plus t divided by 273.15. And we learned in the previous video that when they observed various gases at various temperatures, they noticed that irrespective of the nature or the pressure, this, when it was extrapolated, it met V0 at 273.15. So the first graph is basically, one more thing. We get a straight line which is obtained when we use the equation, and when it's extrapolated, all the lines intercept at minus 273.15. But if you notice, the slopes on the other hand are different for different gases. So the slope value will be different based on the pressure of the gas, but they all meet at 273.15. So we notice that they're straight lines. So this graph is between the volume and temperature in degrees Celsius. So when it's in degrees Celsius, obviously we would have extrapolated, and that's the graph over here. And we and P1 is which is having the is the lowest pressure, has the highest slope, and then you have P2, then P3, which is lesser than P4. So P1 has the least pressure, whereas P4 is the highest pressure. Now this graph is a graph between volume and temperature in Kelvin scale. We've directly used the Kelvin scale, and here if you notice, you don't have to extrapolate because 0 Kelvin is the absolute zero temperature, and that is basically minus 273.15 degrees Celsius. So volume versus Kelvin scale is going to be a straight line through the origin. With that, we're done with the graphical representation of Charles' law. In the next video, we will be discussing the in-text question, which is that.